So, in last class we have discussed about the basic tools in the laboratory. So, mainly we have discussed the length measuring tools with the screw gauge and slide calipers. These are very useful, and all the time we need in our experiment, because one experiment means is the combination of many different measurement. So, this length measurement is frequently used for many experiments. Okay. So, next I will discuss about the most again this most important apparatus, basic apparatus which are used in laboratory very frequently. So, these are the basically galvanometer, voltmeter, ammeter and multimeter. So, the very basic apparatus are used in the laboratory. So, we should know about it, and I will try to show tell you about the basic principle of this instrument, and I will open the instrument and try to show this inner side of this instrument. Okay. So, this just I have shown you here this galvanometer, ammeter and voltmeter. So, it is from our lab, it is the basically from our lab. So, this the I think voltmeter, here it is a voltmeter, then this is the ammeter and this is the galvanometer. Okay. So, this is actually we have taken picture from this instrument. So, this apparatus just okay, this part. So, it is in our lab, from our lab. Okay. So, this is the galvanometer, moving coil galvanometer is called moving coil galvanometer, moving coil galvanometer. Okay. So, I will discuss about the principle of this moving coil galvanometer. So, what is the use of this galvanometer, that is known to you. If you want to measure the deflection, okay, in the circuit, current is flowing in which direction, current is flowing in which direction, or whether current is flowing in the circuit or not. Okay. So, to know that so we use this galvanometer, or what is the amount of current flowing through the. So, that is that also one can find out from galvanometer. So, but mainly we use galvanometer to know the direction of the current, yes, and then to know the amount of current flowing in the circuit. So, there we use this ammeter. So, this galvanometer and ammeter is connected in the circuit in series, okay, in series. And if you want to know the voltage drop in your circuit, okay. So, what is the voltage drop across a resistance or in your circuit. So, between 2 points. So, then we connect this voltmeter, okay. We connect this voltmeter, and this voltmeter is connected between these 2 points in parallel. So, ammeter is connected in series, voltmeter is connected in parallel, okay, in the circuit, galvanometer is connected in the series. Okay. So, these are the it's well known fact. Now, this you know also that this ammeter and this voltmeter is nothing but the galvanometer. This is the it is basically galvanometer. So, galvanometer is converted into ammeter or it is converted into voltmeter. So, how it is done? So, that also you know that when you connect a shunt, okay, means a very low resistance in series in parallel with the galvanometer, then it becomes a ammeter. When you connect a high resistance in series with galvanometer, okay, then it become a voltmeter. So, basically ammeter and voltmeter. So, it is nothing but the mainly it is galvanometer. So, in one case we are adding a shunt in parallel, the shunt that value is very small, and we are adding a high resistance in series with the galvanometer to get it function as a voltmeter. Okay. So, now we want to know the this principle of this galvanometer, moving coil galvanometer. So, that is the principle of this ammeter and voltmeter, because in addition only we have to add resistance, small resistance and high resistance, one is in parallel and another in series to get this to other two instrument. Okay. So, let me open this galvanometer. Okay. So, I will not open this one, but exactly I have another one. So, that is not working. So, that I have opened, and let it be, I think this I do not need now. So, I think yeah. So, exactly I have another one. So, basically I have another one, okay, this similar DC galvanometer. So, these are same as this is the same as this one, okay, but this I just opened it to show you inside what is there. So, this is the cover. If I take out this cover, okay, let me take out this cover. Okay. So, let it be there. I think I will just keep it to show you. This is the cover, and this is the, I think whatever the scale. Okay, this scale was basically here inside. Okay. So, but earlier I just opened it, because to open it, it takes time. So, it will be wastage of time to open it here. So, just I have opened it earlier to show. So, it was basically here. Okay. So, I think here this is. So, from inside one can put this, inside one can put this. Okay. So, that is okay. So, this I have opened it, fine. So, this let me keep it here. Okay. So, then inside what was there? So, this one. So, it is basically here, you know, this, it was this way, it was this way, and also it was this way, this scale was there. So, on top of it there is a, yes, I think I have to put it like this. Okay. Yes. Okay. So, this it was inside of this box. Okay. So, I do not need it. So, this is the for scale, this is the indicator. Okay. Okay. So, now, so this find what is this very small parts inside, you know. So, this is called moving coil galvanometer, because this principle is based on this, on the moving of a coil. So, where is that coil? Where is that coil? I have to show you where is that coil. So, I think it is here. I have to show here two parts is there, you know, one is moving coil, another is permanent magnet. So, I am taking out this one from here because earlier just I opened it. Okay. So, this is the permanent magnet, I will discuss about it. So, keep it here, and this is the another parts of moving coil. Okay. So, here now clearly you can see, here now clearly you can see this some coil is there. So, this is the coil. Okay. So, I think you can see it, this is the coil, right. So, I think I can use this magnifying glass, and but it is not, you know, but yeah, if you focus then you can see this clearly, this this moving coil. Okay. So, this is the coil, rectangular coil you can see, right. Okay. And this one is cylindrical. So, this some soft this magnetic material basically, this is not magnet. So, its permeability is high. So, it will helps to increase the lines of force, magnetic lines of force, but this currently forget. So, this the coil. Okay. So, this coil can move, this coil can move, and this indicator is connected with this coil. And now, this coil, you see on top and bottom you can see this the spring kind of things, you know, this is the spring kind of things. Okay. This is the spring at bottom, and top also you can see this, spring. Okay. So, two springs are there, one is at the top of this coil, this rectangular coil, and another is bottom of this rectangular coil. Okay. So, what does it mean? It means that when this coil rotate, okay, when this coil rotate, so spring also this you see this, it is called the spring also, it is twisted. Okay. So, there will be restoring force on this, there will be restoring force on this on the rotation, due to the rotation of this coil, not coil, it is the rectangular coil. Okay. Due to the rotation of the rectangular coil. So, there will be restoring force or torque to bring back in the original position. So, the two force will work, two torque will work here. One is this from the rectangular one, this rectangular coil, and when it is in magnetic field, permanent magnetic field. So, that I will show you. So, there will be torque on this coil, and because of that it will rotate, Okay. Indicator also just move, and when it rotates this spring, it will be twisted, and then there will be restoring force, it will be twisted, there will be restoring force, and that force will try to take it back. So, it will be at a final position where these two force, one is from this torque on this torque from this rectangular coil, another is restoring force from this or restoring torque from this spring. So, at equilibrium position they will be equal. Okay. So, that is the balance equation, and from there basically one can understand the rotation of this indicator in terms of if we tell theta fine. So, that I will discuss. So, this coil is basically you have to put in this the magnet, you see this the magnet, you see this the magnet. Okay. It is quite strong permanent magnet. Okay. So, here it is a horseshoe magnet, you know. This basically magnet is here, this one. Now, these two are pole, this circular pole, you know, these are pole. So, it's called horseshoe magnet. Okay. So, here magnetic field is basically radial magnetic field we will get. Lines of force is along the diameter, along the diameter. Okay. So, if you take just two pole pieces, two piece, okay, just rectangular these two piece if you take. Okay. So, then between the two pole piece, if it is rectangular, okay, the two pole pieces are parallel to each other. So, you will get lines of force magnetic field like this, magnetic field like this. Okay. Now, in this case you are getting magnetic field basically along the diameter, along the diameter. Okay. So, magnetic field is not in a particular direction, it is basically along the diameter, along the diameter. Okay. So, in all directions magnetic field is there, in all direction of the magnetic field in okay, from the center you can tell in it is in all directions. Okay. So, so this is the radial magnetic field, this is the radial magnetic field, not just like parallel pole pieces whatever it gives the magnetic field in a particular direction. So, there is reason why here it is that circular pole horseshoe poles is used. So, that also I will explain. Now, this you have magnet, permanent magnet which is giving you radial magnetic field. Now, this is the center of this one and center axis of this rotation of the coil, axis of this rotation of the coil, this basically this the axis. Okay. Now, this here when I will put, so these two center, this axis here and axis here. So, this basically it is the same line, say coincides. So, when I put here, so that means my circular coil it is free to rotate. Okay. It is free to rotate about this axis, Okay. Now, here what I am just doing, I am putting this coil, it is the moving coil, it can move about this axis, it is in a permanent magnetic field, radial field. Okay. And this moving coil, it has at top and at bottom there are two spring. Okay. Two spring is connected and this pointer it is attached with the rectangular coil. If rectangular coil moves, so that movement is showed by this pointer. Okay. Now, when it rotates, pointer moves, okay, but there is a restoring force given by the spring attached with the rectangular coil at the top and bottom. Okay. Now, current, so externally there are see two I think this I will show you. Okay. So, this externally when it is connected, so basically these two black and red, positive and negative, okay, when you are putting in a circuit in series. So, current will enter. Okay. So, red one say it will enter. So, it will enter from the so this one is connected with the one of them is connected with the basically top spring and another is connected with the bottom spring. Means current will enter from here, then through the top spring it will go and this top spring is connected with the rectangular coil. One end of the coil, this coil is nothing but the so it is basically just a wire, copper wire, insulated copper wire, and that then make it rectangular. This many turns of that will give you this coil. So, that current will enter into this coil from the top through top spring, and then at the end of this coil. So, it will go out the current from the coil to the bottom spring, and bottom spring that end is connected with this other one. Okay. So, that way it will complete the circuit. So, that means current will pass through this coil. Okay. So, this coil, it is a moving coil, it is able to move, and this coil is in a magnetic field, and now this magnetic field is now this when current passes through the coil, then this, I think I have to put properly because these are, yeah. So, when current passes through the coil, then depending on the direction of the current in the coil and magnitude of the current in the coil. So, this coil, it's just rotate, okay. And so this amount of rotation, it will depend on the amount of the current. So, that is why, so this helps to know the direction of the current and amount of the current passing passing in the circuit. Okay. So, let me now I showed you, now let me describe it. Okay. Theoretically. So, now I have to find out basically when the coil will rotate in a magnetic field, when current will pass through the coil, then there will be torque on the coil. Okay. If there is a torque on the coil about an axis, then coil will rotate. Okay. When coil will rotate, it is attached with the spring. So, there will be restoring force in equilibrium. So, these two force or these two torque we have to equate. Okay. We have to equate, and then you will get the balance equation. Okay. So, now let me tell you this how this torque is coming, torque is acting on the coil. Okay. So, I think I will just calculate here. I have, yes. So, first two things I will discuss. One is you have a coil, right? You have a coil, rectangular coil. You have a rectangular coil. So, there are many turns in this coil, just let me show few turns. Okay. Okay. So, now this is one end of the, this is another end of the wire of this, which is used for this making this coil. So, this is connected with a spring, okay, with a spring. This is also connected with a spring, just rough drawing I am making. So, now this is connected with the positive end, say this power you are giving battery, say it is a negative electrode, right. So, current will pass through it, say okay, this other way current will pass through it. So, current will pass through this coil and then come out. Okay. Now, you know this current carrying conductor when it is in magnetic field, so it feel force. So, there is a force, there is this current carrying conductor feel force, and that force F equal to I think this the yeah, B cross I d l, I d l, B I d l, B I L, okay, B I d l, or yeah, I think this force is like this, okay. Okay. So, now this B, this is basically is coming from the permanent magnet. So, if you take permanent magnet, these two pole flat pole pieces, this magnetic field will be in this direction. So, generally we draw like this, two flat pole pieces. Okay. So, then magnetic field is like this, uniform, it is in say uniform magnetic field is like this. Okay. So, this is the direction of the magnetic field, this is the direction of the magnetic field, okay, B, and when current is flowing through this arm, you can see this the direction of the current is in this direction. So, it is coming this way then, okay, it is in this arm is downwards, current is in downwards, okay, and in this arm it is upwards. So, in this case current direction is this, okay, right. So, now here force direction will be, so this is the cross product, okay, okay, B cross I dot I d l, okay, or I d l cross B. So, I did not remember, but I d l cross B maybe, yes, but whatever the case. So, now here this is the direction of B, this is the direction of the current. So, this I, okay, I d l. So, what is this ideal? I will this is called current element. Okay. So, its direction is taken this in downwards. Okay. So, then force. Okay. So, this cross product, this force direction will be either upwards or downwards depending on this, okay, IDL and cross B, fine. So, this on the other arm what is happening? So, this magnetic field direction is this, the same direction as this one, okay, but current element, that is the direction is this. So, direction is this. Okay. So, it is just opposite of this other arm. Okay. It is just opposite than the other arm, whatever here. So, here you can easily tell if this force for this case, okay, if it is upward, so in other arm it will be downward. So, exactly you have to find out from this, you see some rules is there. Okay. So, from there if it is upward or downward, that one has to find out, but it is clear here, if one is upward direction, then other one will be in downward direction. So, basically you are getting force like this. So, here one is in this direction and other one is in this. So, two force like this, here basically two force are working, one is say if it is this way, at this other distance it is in this way. Okay. So, two force are working. So, two force are working at a perpendicular distance of say B. Okay. So, then torque will be this F cross B, right, torque will be F cross B. Okay. So, this is the force direction, and this is the B direction. So, this torque direction will be in third direction. So, one is this, another is this. So, third direction is this. Okay. Third direction is this. So, torque direction will be this. So, torque, in case of torque, this direction is basically axis of rotation. Okay. So, about the axis of rotation. So, as I showed you this is the axis of axis of this coil. Okay. So, about this axis of the coil, because of these two opposite force, this is the it formed the couple, you know, and due to this couple, so it will rotate about this axis, it will rotate. Okay. Now, what about the other two end? here in this case you see this magnetic field is in this direction, magnetic field B is in this direction and IDL, this current element also in this direction. Okay. So, they are in same direction. So, cross product is 0, right, sin theta, theta is 0. So, it is 0. So, here also it is the same, it is the same direction, but in opposite but so minus sign will become, but it is 0. So, plus sign minus sign does not matter. So, there is no couple from this on these other two arms. Okay. So, thus it is. So, only magnetic field on the parallel to this area of the coil, it will give you the torque basically, and any other this, if it is a perpendicular component of this field will not give any torque. Okay. It will, so perpendicular, current is in this direction, say current is in this, it is perpendicular. So, I think third direction is this one. Okay. Perpendicular field, if it is perpendicular to this. So, I think this, so this, so it is the torque is in this direction, not torque, force is in this direction, other force in this direction. Okay. So, in that case this force is basically on the same line, along the same line. So, they will cancel each other. So, there will not be any couple. Okay. So, there will not be any torque, right. So, so only planar field will give you. Now, I will explain. Now, you see, now imagine, now it is about this axis, it is rotating. Okay. So, magnetic field is in this plane. So, now it is rotating. So, now magnetic field, now it is not parallel to the plane. So, it has some angle. So, you will get, so you can resolve it, get two component of this magnetic field. One is on the plane, another is perpendicular to the plane. Okay. So, effective magnetic field will be only this parallel component parallel to this plane, right. So, now this torque, okay, now effective B is now it is smaller, because you are getting only component. Okay. So, then basically your torque will change when it is rotating. So, for each rotation it is torque, magnetic field is changing, effective magnetic field parallel to the plane it is changing. So, you will get the torque is changing, means torque is reducing. Okay. So, that is what that we do not want. We want that torque should be constant, even if it is rotating, torque should be constant. So, that means B should be constant, B all the time we should get B, same B on the parallel to the plane. So, that is why we are taking here, we have taken the circular, we have taken, instead of this flat pole, we have taken circular pole, we have taken circular pole, we have taken circular pole. Okay. In case of circular pole, this magnetic field is basically radial field you will get, sorry, radial field you will get, radial field you will get, radial field. Okay. You will get radial field. Okay. When it is radial field, wherever this coil is moving, this coil is moving, so in radial field. So, magnetic field all the time it will, you will get along the radius, along the diameter. So, effectively you see, for a particular position, so magnetic field is now along the radial. Okay. Okay. So, I have coil, I think, say I have coil. So, now coil is rotating, So, how to show you, coil is rotating like this, okay, you have radial field. So, parallel to the plane there is a magnetic field, parallel to the plane there is a magnetic field. Now, other magnetic field are not parallel to this plane, but this both side they will give some component. Okay. So, but main field is parallel to this plane, that is there. If it is rotate, in different direction, all the time main field along parallel to the plane it is there, because it is radial, and from other components. Okay. So, this some component from other radial field you may get parallel to the plane. So, that will be more or less it is the for all position, that component part also will be same. Okay. So, this radial field is basically during the moving of the coil, all the time it is giving the constant magnetic field which parallel to this plane of the coil, and thus this torque will be constant during the moving of the coil. Okay. So, this torque, because of this torque it will rotate, and then you are taking basically this basically B I d L or L into B, this basically this is the width and this is the length. L I can write basically this d L, instead of d L I can write length, this the length, and this is width. So, I B I L B, that will be torque. Okay. And then this torque will be balanced by the basically restoring force, restoring torque. Okay. So, that restoring torque is basically this, it can be two types, it come from spring here. So, it can come from the this is a torsional, it is called when this coil is hanged from a fiber kind of things. Okay. So, this it twists. Okay. So, this is called torsional torque. Okay. Torsional constant. Okay. So, spring constant. Okay. So, this in this case for per unit length, and this other case per unit angle. Okay. So, that is the constant K. So, here one can convert from length to angle, you know, this L theta, I think, yes, theta into radius, r theta will be L, r theta will be L. Okay. So, one can convert from length to the angle also. So, anyway, for torsional torque constant or spring constant, so one can write it is the this torque is basically K theta. Okay. So, from there, so this basically this rotation of this coil means rotation of this pointer, whatever I showed you, rotation of the pointer, rotation of this pointer. Okay. Rotation of the pointer, that is basically proportional to the B magnetic field. It is constant for permanent magnet, it is I is the amount of current. So, this only this is variable, L, B, all B, this breadth. So, these are constant only. So, this theta and K also is constant. Okay. Spring depend on spring. So, I is proportional to this theta. Okay. So, and of course, direction of this angle, it will depend on the direction of the current. Okay. So, that is the measurement, this rotation of the pointer, it depends on the amount of the current and direction of the current. So, this is the principle of the basic principle of the moving coil galvanometer, right. So, so that is what galvanometer, which will be used in our laboratory, and I have opened the things and showed you and match with the theoretical part. Okay. So, I think yeah, I will stop here, I will discuss in next class. Yes, thank you.